There are times that a solution to a differential equation is either difficult or impossible to obtain, or we just need approximations to points on the curve, and in such cases we use what we call numerical methods. This set of videos is about one numerical method called Euler's method. It's based on the fact that if we have a slope y prime defined as a function of x and y, so y prime equals f of xy, and a known point on the curve that we call an initial condition y of x naught equals y naught, then the equation of a tangent line to the solution curve at that point is y equals y naught plus f of x naught y naught times x minus x naught. And this is really just based on the point slope form for the equation of a line. Y minus y naught is equal to m times x minus x naught. And in this case, we're representing the slope as f of x naught y naught. The resulting equation is known as the linearization of f at x naught y naught. It's also sometimes called a linear approximation. Now you might have noticed y prime equals f of xy with y of x naught equal y naught is actually an initial value problem. To help see how Euler's method works, we're going to look at a graph. We have here the xy plane on which is a blue solution curve. This would be the result of solving the differential equation, or the graph thereof. We're not so concerned about the solution curve right now. It's just being used as a visual aid. Y of x naught y naught gives a point on the curve x naught y naught. At that point, there's a tangent line. The tangent line has a slope given by f of x naught y naught. Now, if we consider the point x1, y1 with an x value that is x1 equals x naught plus h, a small distance to the right of x naught, then we have y1 is equal to y naught plus h times f of x naught y naught. This is a y value that's given by the tangent line to the curve. And remember, f of x naught y naught is rise over run times h, which is just run, plus y naught gives me a new y value. In other words, rise over run times run is rise. Rise plus a previous y value is a new y value. The resulting point x1, y1 is an approximation to the point x1, y of x1, which is the actual point that's on the solution curve. So using the tangent line, we now have an approximation to a point on the solution curve. If you need to, run back through that explanation a couple of times, and I'm sure it will fall into place. Now, using the point x1, y1 and the slope given by y prime is equal to f of x naught y naught, xy, at that point, we can find a new kind of a tangent line that goes through the point x1, y1. And it's not really a tangent line because x1, y1 isn't on the solution curve, but it is an approximation. I should probably tell you, this h that we're looking at that separates x naught from x1 is intended to be really small. We're talking about like 1/10, 100th, 1,000th. And so this horizontal distance is very small. This vertical distance is pretty small, and so we're working with, something that's a reasonable approximation. Now, let's look at what we did. We started with x naught, y naught. We traveled along the tangent line, and we found a point x1, y1, where y1 is an approximation to the y value on the solution curve. We're going to repeat the process with another h away from x1, and we're going to come up with a new point that's on the quote-unquote tangent curve that's going to be x2, y2. Continuing this process over and over, we're going to find points that are approximations to the solution curve, or rather points that are approximations to points on the solution curve. Now back to the sentence I had started, using the point x1, y1 and the slope that we have, which is f of xy, we get y2 is equal to y1 plus h times f of x1, y1. And we get the point x2, y2, where x2 is x1 plus h, which means it's x0 plus 2h. This process continues, and we have a generalization of the results. X sub n plus 1 is a previous x value, x sub n plus h, a horizontal distance. A y value, y sub n plus 1, is a previous y value, y sub n plus h times f of x sub n, y sub n, the slope at the point that we had just generated. This is called a recursive formula because we need to know xn and yn before we can generate x sub n plus 1 and y sub n plus 1. Let's see what this looks like using an example. We're going to use Euler's method. We're going to get a 4-decimal approximation of the value y of 0.2 for the differential equation y prime equals x plus y squared, with the initial condition y of 0 is equal to 0. We're going to do it twice, first using a step size of 1/10 and then using a step size of 5/100. Our initial condition gives us that x0, y0 is equal to 0, 0. Using a step size of h equals 1/10, we first note that y0 is equal to 0, and then we want y1. y1 is equal to y0 plus the step size 0.1 times f of x0, y0. Now that f of x0, y0 is given by the differential equation, right? So f of 0, 0 is 0 plus 0, and what we see is this first step is pretty boring. I've got news. This first round of computations is not going to be exciting. y2 is equal to the previous y value plus the step size 0.1 times f of, now we have a new x value, it's 0.1, and the y value is 0. Why is the new x value 0.1? Because x1 is equal to the previous x value 0 plus 0.1, the step size. y2 then turns out to be 100th, and now let's put some stuff together here. x0, y0 is 0, 0. That was the initial condition point. No mystery there. x1, y1 is then going to be the point 0.1, comma 0. x2 is x1 plus 1/10. And so x2 is 0.2. The y value that we got associated with that, the approximation, is 0.01. So now we have the point 0.2, comma 0.01. That y value is an approximation of y of 0.2. So now we're going to say y of 0.2 is approximately 0.01. I don't think that gave us a lot to think about. That's okay, we're going to do it again, using a step size of 0.05. Associated with x0 equals 0, we have y0 equals 0. That's our initial condition. We're starting the process all over again. But we're still using the differential equation y prime equals x plus y squared. x1 is equal to 0.05, one step size bigger than x sub 0. y1 is equal to the previous y value of 0 plus 0.05 times f of x0, y0. F is x plus y squared. x0 and y0 are both 0. I'll put them in here just to be formal so you can see where everything goes. And we see that y1 is equal to 0. That associates with the point 0.05 comma 0, and it looks like it's not very exciting still. Sit tight. x2 is 1/10, one step size away from x1. y2 is the previous y value of 0 plus the step size times x plus y squared, so times 0.05 plus 0 squared. This gives us 0.0025, and the point x2, y2 equals 0.1, 0.0025. Now that's not what we're after, but I'm writing that down so that you have the context. x3 is 0.15. y3 is the previous y value, 0.0025, plus the step size of 0.05 times x, 0.015, plus previous y value squared, so 0.0025 squared. Doing the math, we see that x3, y3 is approximately 0.15, comma 0.0075. One more time, because folks, we found the y value, or the approximation, associated with x equals 0.15, but what we want is an approximation for the y value associated with x equals 0.2. x sub 4 is 0.2. y sub 4 is equal to previous y value, 0.0075, plus step size of 0.05 times our x value, 0.2, plus previous y value squared, 0.0075 squared. Doing the math on that gives us that x sub 4, y sub 4 is approximately 0.2, comma 0.0150, which then gives us that y of 0.2 is approximately 0.0150. That's the approximation that we were after. Notice that 0.0150 is close but not exactly the same as 0.01. When we have a smaller step size, our approximations will tend to be more accurate.